Okay. Okay, how was the week two? Is it going fine? Like, what kind of doubts you have? Okay. So, like, what do you want uh, from my side to cover? Like, what is your expectation?
You will introduce with some new concepts or the things
Sorry,
that
can you
we
speak a little
might
louder? Yeah, Ritik, maybe you can speak a little louder.
Sir, I am saying, sir, the week two, week one are pretty good chapters. You can introduce with the new concepts or the things that we might get confused during the exam.
Confused during the exam. Okay. Mm, yeah, go ahead.
Uh, so regarding that part, how Taylor series approximation helped us in getting that gradient descent updation. Actually, the lecture was almost fine, got the things, but if you could put or throw some light or intuition on that, how we come to that part.
Uh, okay. So, have you ever come across Taylor series before?
Not like that. Recently, when we were doing calculus in higher secondary, there few times, but
Uh-huh.
before after that I can't remember exactly. Like I encountered this in that gradient descent.
So, in MLT, MLF, where maths too.
Maths 2 I'm not sure about. uh, MLT it was not there. uh, MLF maybe I have missed. I didn't that went through all the lectures in MLF. MLT I'm sure it was not there.
Mm, okay. Okay, we can go through it. Not an issue.
Okay, sir.
Okay. Um, Anything else you want me to cover?
In continuation to that, if you could also give some more intuition for us beginners about that approximation of continuation functions, like that concept where we use multiple bars or bins to approximate any continuous functions, that universal approximation thing.
Okay.
actually
So,
ac- Actually the visualization was clear for a beginner, was able to get the things, but if you could uh, throw some light that uh, as a blank mind or as a beginner, how someone could approach that problem and can go with that kind of solution. Actually it is a very new kind of approach and solution I encountered, like that.
okay. So,
Yes.
okay. I'll go there and maybe talk about it.
Okay, sir.
Uh, Let me share my screen. Um,
Sorry to interrupt, sir. In the above, where it was the proof of the convergence, can you comment once again about that delta, where it was taken as the minimum of the dot product of the W star and that thing?
the blue star or UT
In the
and
proof, yeah, in the proof of convergence.
uh,
Uh,
okay. Uh, Proof of convergence
percep-
of
yes,
perceptron.
Yes, sir, this part.
This part.
Yes, sir. If you could comment in short about the range of that delta and how can we relate that delta to the margin thing?
Um, okay.
Like it has
Um,
been shown that delta would be the minimum of that, the dot product of the optimal W and the data point. But if like
no, see,
uh,
no, that is not there. So what we assume is that when we make a correction, we add delta quantity, right? So you can assume anything as delta, a small quantity also if you can assume. But if we do it multiple times, it will grow, right? It will grow to some level. But how much this whole quantity can grow? That is the there should be some limitation. Otherwise,
yeah,
this will become open-ended question, right? Then it will not be bounded by anything, and that's an
yeah,
issue. So it is actually bounded by this cos beta, right? So no matter how much you add, you can, let's say also k times delta. Delta you can consider some positive value. Okay, some small positive value you can imagine,
yes, sir.
0.05, something like that.
Yes, sir, that part, like as you mentioned, that delta would be some positive value. So
Yeah.
delta has been mentioned as the minimum of that dot product of W star and PI. So how we came to that conclusion that it would be some positive value? Like we are
Um.
commenting indirectly that the minimum of the dot product will always be positive.
See, let's say you wanted to consider something which is growing, right? So you want to have a higher something, like you don't want it to grow more than some value, right? So you know that it is going to increase, so you can assume that it's a positive. If something is reducing, that's how you wanted to think. Then you can say that it's a negative, so I'll be subtracting repeatedly, and then I'll reach a point where I can't go beyond that small lower value, right? Since we wanted to add it, I'm assuming that it's a positive value, or you want to increase it, right? So if it's a negative value, then there's no point of this assumption. So you wanted to increase it to some level, and then you want to think that, okay, where it will limit itself, right? Where it will stop, not going above it. So that's why you have to assume it as positive only.
Okay, like so that since we were increasing, like
Yeah, so it will increase to some point. That's what the assumption is, right? That it will how it will increase. It will not increase if it's a negative value. So it has to be positive. Otherwise, uh, I mean, it can go like zero or negative. That is not the idea behind it. We wanted to increase it, and then we want to think that, okay, it will increase. At some point, it will reach. Then it will not go beyond it. So that the higher point is what, that is the idea. That what is the range of this whole thing? How much it can go? Um,
oh,
so you have to assume it as positive only. Then this thing will make sense. If it's a negative, then we are not much worried about, if it's, even though if it's a negative. So we are only worried about the points where it can blow the system, right? So all this thing comes into picture, and then we constrain all of this, and like it become an optimization problem, and then we can solve it.
okay. So regarding the lower limit, logically we assume that it would be a positive quantity, and regarding the upper limit, we went with that cost thing, and so with that cost boundary, we also got
Yeah.
that upper thing.
Yes. So from
O-
costs, we know that it has to go up to like one or something, right? So it will not go beyond it.
Okay,
Maximum value it has is one.
one small thing just to confirm, sir.
Hmm.
If you could scroll again that minimum part delta. So what I was approaching this in that way, that to comment on the delta that it would always be a positive value, since it was the minimum of that dot product of W star and PI. So when we
Hmm.
are doing the dot product with W star, so W
Hmm.
star the optimal one which correctly classify. So since
Yes.
we have taken W star, so it has always to be greater than 0. That is the case now when we don't need to rectify. It was the case W transpose Xi should be greater than 0.
Uh, yes.
Like we are
So,
doing the correction and W. Yes, sir.
uh, so what is the doubt in this? I didn't get the doubt part.
Actually, I just wanted to confirm if I'm also approaching this in the correct way, like how I was trying to comment on that delta will always be positive.
Okay, okay. So you understood it? Uh,
Yes, fine.
okay, fine.
Yes, sir. Thank you.
Mm, that's something to be. Okay, so mm, the first one is that okay, related to the data series. Uh, okay, here it is. So before that, before we go to that, yeah, it's okay. So let's say this is a loss function. Okay, you can assume any loss function. But just for simplicity, you can consider any convex loss function which has uh, global minima and local minima both are same. So let's say you are at this point. Okay, this is a loss function value, you know. Um, but you so actually what happens in machine learning or deep learning is we have given a data point, right? So x and y is given to us. So you can consider x as a multi-dimensional also in some higher dimension, but these are the points given to you, and if you actually plot it, it will be a point, right, in any dimension, but it's a point, and it has some like label to it, or 1 0 2. I'll just consider it as numerical, so 0 1 2 something like this labels, right, and that's how it is there. So they are points, right, something like this, uh, like let's say this, right? Now any kind of algorithm which or any kind of function which f of x you can consider, uh, so this will be approximation of uh, y, right? So it has to be very near to y, or it has to be equal to y. So we are now approximating, we are not saying that it has to be equal to the y, right? That is not the case, we are approximating. So uh, that is the that is the point, right, that we wanted to approximating the things now. So what we'll do is we will have maybe, let's say this kind of um, function that is f of x. I can get this kind of function, or you can get any kind of f of x. But the thing is, we know only about um, certain points, and we don't know much about it. So actually, we don't know the whole function, right? So we don't know at every point in reality. We know certain things about the function, that at this point these values are there, and like that. Okay. So this is what f of x is. But from this, we will uh, go towards a loss function. So this loss function is this one. So this is a loss function. Okay. So let's say you got this kind of loss function, um, and we what we know is, let's say this x values, and this w values, some w1. I'll just say w1 and x. Okay, so this all produce some loss value. Let's say L1 they produce, right? And now what you can do is actually you can't control x because that is what you got as a data, but you can control w. So you can control it and you can change it, right? So let's say you just change it. Why you did it, how you did it, that's different thing, but you changed it to something and you got L2, right? It could be anywhere in this function and something like this. So you can get more of this, right? But so how will you know that is w1 is better or w2 is better? You don't know that. You can't uh, not yet, but what you can do is uh, you can maybe compare both of them. Say, so I want lower um, something like this, right? So let's say L2 is, if L1 is lower than L2, then this not bad, this not good, but this is good, right? Something like this. So that is the whole idea behind that. How will I know that which direction should I move into, or how will I know that where should I go in the loss function? Because I know only one point at a time, right? At a time. So when I knew L1, let's say I knew W1, right? I knew W1. Somehow I started with some point. I said that W1 are this, and X I already knew. So that's how I got this point. So now I have the function? No, I have one point. That's all I have. Nothing I have in reality. I don't even know how the loss function actually looks like, right? Because I only know one point in it. So how will I know that should I go this side, there, here, or anywhere? I don't know. But then the savior comes as Taylor series. It says that okay, since we don't know where to go, what you can do is Taylor series says that a point very near to the point I know, right? So this point I know. You can maybe consider as W, which I know, but a very small, very some kind of range, right? In that you can maybe say this range. We can actually approximate the value. We can actually find the value, and the approximation can happen with Taylor series approximation. That around this point I can find the values. So let's say I can find value here, here, there, or somewhere. I can do it, and that's where I wanted to move, right? So I wanted to move from here to there. How will I do it? So that movement part will help by Taylor series. So this all things require Taylor series to do it. That I wanted to move somewhere in the like d dimension plane, or maybe in loss function maybe you can not, it's on d dimension, it's like some w's, but w's are also not um, one, like let's say w1, then w2 is there, could be w3, w4, right? So multiple dimensions could be there, and then the loss function is there in all this dimension, right? So that's how I'm talking about now here, d. Okay, or anything d plus one, something like that. Then bias is also there. So you wanted to go towards the minimum. See, we actually don't know what is the loss function looks like. We know one point, and we wanted to go down and like maybe find the best minima we can find, right? So how we can do is we can predict or approximate a value near the point I know. So near the point I know, that is what I wanted to find. So I'll use Taylor series. Okay. So so what happens is I W naught, I know the value. Okay, so this W naught is the one where I initialize the weights. I know this value is here. Okay, you can say this is the point I know. I didn't know this loss function actually. Now what I'll do is I wanted to move by something like, let's say please find at W. How will I do it? So at W naught I know that loss I can do. I'll do a first derivation, right? So maybe I can say dow L by dow W, something like this you can consider. So for this first derivation, and then you have to do like W minus W naught or something. What is the difference, right? What is the distance between this? So this is W naught. I wanted to let's say uh, predict a value or approximate a value, that what will be the loss value at this point, right, along this thing. So how will I do this? So first I'll maybe find a difference also. So that's what this is. I'll do the squaring, and also how does Derivation comes up, that is a different um, thing altogether. But this is what Taylor says approximation is, right? So maybe you can remember the formula. The derivation is a little different, right? So this Taylor series came up to it. If you wanted to see the derivation, how why this is the only formula, you can maybe check out the YouTube. But this is what a formula is, right? That you take w minus w naught, w minus w naught square and cube and so on, right? So it will go up to any number. Okay, it's not limited. It goes to infinity. So as much as more and more you add these terms, you will actually approximate it better. Okay, so maybe using this one term, like that is this value. But if you add little bit, you might move here. Then if you add, let's say, two terms, this one and this two terms, maybe you can predict much better. Three terms much better. So this will improve your prediction by this. But the good part is that we don't have to go up to infinity to predict it. Even though we have one approximation of linear approximation, it works well for, let's say, linear functions works well. For quadratic functions, also, like approximation to one, it works like better. So we have this thing. I think I remember. I can. So yeah, see, this function is there. So this is the part where I'm trying to approximate, right? So this is what you can say, maybe W, and this the black dot is this middle black dot is a W naught, and the range around I can assume, right? Approximate. So you can change the epsilon, that the higher you go from the point, then you won't be able to approximate. So this is a linear approximation. If you go quadratic, then it will the it won't be a linear line, right? You will have line of two variables, something like that. So that's why you can do a better approximation as you increase this n. But that is not we want to do, because n equal to 1 is like more than enough. We will have much more complicated derivations to do. Then we'll do gradient descent, so that we can do it. So let's say I'm here, I want to move here, I'll just take small step. So that's why the step size is very important. You might remember from MLT also that step size is very important, that don't choose much bigger step size, otherwise you will blown off, right? So the step size is, and something or this gradient is coming from this equation. So this is what you get for gradient descent, right? You would have learned, wherever you learned gradient descent, this is the same idea of that how why you wanted to do gradient descent only, or not something else. Because you wanted to reduce the loss function, and that reducing the loss function is means I wanted to know the loss function at a point somewhere other than like this point, right? So somewhere other than this point, how will I know? Linear, this Taylor series will tell you. So that's how this Taylor series come into picture.
Okay,
Okay.
so we were looking for very small step it was. That's why linear approximation will work absolutely fine there.
Yes. Yes. This very small step size, or very small this thing we are looking for, and that's what this linear approximation will give. You can do quadratic approximation, but that is not I mean, it in the whole deal, like experimentally they have done using one only, and it has worked, right? So not needed to go to quadratic approximation.
Yes, sir.
Now, okay, so that's how this thing is coming up. So at nu,
And you, that is small thing. Okay.
yeah, so small thing, right? Delta theta. Now, um, the change, right? So that's where you wanted to approximate the value. How will you do it? So you will use this approx linear, so this Taylor series, and you say that, okay, so now the squaring is happening, cubing is happening, since n is very small, right? So let's say if it's 1/2, then after like squaring it, you will get 1/4. If you cube it, 1/8, 1 by 16. So at some point, like, I'm not saying that n is 0.5 only. It could be lesser than that also. So it will eventually goes like 0, right? It will be very small value, or it will not contribute much to this summation. So
will
that's
not
why
contribute.
maybe you can ignore this and you can have this one part. And now what you want is, you want this new value, right? So what I know is this point. I want another value of loss which has to be lower than this. That's what I'm sure about. That this new loss value should should be
Low.
lower than this point, which I know. So how will I do it? I'll just do this, and from this I get to know that this implies that how that what actually I'm doing is, actually, see, if you see this part is there, I'm subtracting this, so this is the point remaining, and I'm saying that it has to be lesser than 0. So here we have see, we have three things. One is eta. Eta is learning rate. I mean, you will come across it later on also, that eta, and we'll always take it as positive scalar value. Okay, so this is always going to be positive and scalar. Okay, positive and scalar. So scalar means value only. It will not have direction, not like that. Okay, ut is something, um, is the gradient or the direction. So this will give you the direction of it. So let's say you want to remove this side or that side. It will be decided by this ut, or any other direction, right? So this that part is given by ut only, and you can take it as a, gradient or direction, uh, vector, something like this. Okay, and then this loss, this delta theta, L theta, is the derivation of loss at a theta, right? So maybe you can say this. Okay, this is what it is like,
Loss
this
delta.
part. Okay, so these two things are there, just two entities, that this vector in some direction, and then ut, let's say, in some direction. So uh, or or ut is just a direction, right? You can consider some direction, and how much this direction should be, which will be multiplied by eta, right? So this eta will be the controller of this, the length of this, so magnitude of this. Okay, so these two things are there, and now we wanted to move in some direction. Okay, so why it has to be opposite to this, like, let's say this is my delta theta L theta, then why it has to be in the opposite direction, the ut, which is transpose, like, you can consider u only. Okay, so why it has to be in opposite direction? Because of this thing,
To
that
reduce the loss. Hmm.
as much as possible, right? So reduce the loss as much as possible. So if I move in the opposite to the gradient, then I can reduce the loss as much as possible. And here is the proof of that. That will take what, dot product, right? So this is
Dot
what dot
product.
product is
Yes.
of two vector. So that I taken here, and I'll say that I wanted it to be as low as possible. So I wanted it to -1. How can I do it? So have them in the opposite direction. Okay. So that's why, like, -1.
Yeah, the
Um,
minimum we wanted,
the
and
Yeah,
-1 to
negative.
+8.
Yes, yes.
Hmm.
Okay.
Yes,
Uh,
sir. I'm able to connect like how Taylor series was a savior for us.
okay. Yes. So that's how this all coming into it. Maybe I thought it was covered in MLT when Arun sir was taking date in Tison. I'm not sure though. Um, okay. But yeah, so that's how it comes there, and that's how we have this negative, and this eta we uh, assigned, so that we know that um, how much you wanted to reduce this part. Okay, how much
Yes.
you wanted to move. So learning rate, then this are the gradient, and this is the current value of the weights. Okay, and that's how you do the update rule. So this updation will happen, and you'll get new weights and biases. Then on new and weight and biases, you again compute the loss function. Right? You go through everything, and then you get the new point. So this was one point. This was the new point. Because of Taylor series, you are able to find it.
Yes, sir.
Okay?
So for the
And
ease of for to make the visualization easier, the loss function is also drawn there, or the loss surface. But basically, what the actual thing we are doing is, the path we were moving towards the minimum. That was the original thing only we had. We will not have that loss surface with us.
Yeah, we
Like,
don't have, we never have it, right? Because it
yeah,
could be anything. Yeah,
hmm,
we never
to
have
under,
the loss function.
to make us understand, like in visualization we are having that loss surface, so that we can understand that how we were moving towards the minimum.
Yeah, yeah, correct. So something we are doing. That's what. But right, in reality, we don't know what is the loss. It could be like this. It could be anything,
Mhm.
right? Uh,
And Taylor series help us to approximate, like if you want to move in a particular direction, like approximate in a particular position, approximate the function of that value. So Taylor
mm,
series help in that. And considering like in which direction you should move, so we had this one, like to get the minimum we have to opposite of the gradient thing.
yes, yes. So yes, so opposite of gradient is because of this another optimization problem.
Mm,
The gradient or something which is like using the Taylor series approximation.
yes.
Okay.
uh, we need our new loss to be lesser than the previous one.
Yeah, but as much as lesser. So that is the reason of this another optimization problem. Lesser uh, is something you can get between any point, but as much as possible is the new thing. And this UT is the one which will give you the direction of it, that where you should go to get this lesser part. Okay.
Yes.
So that was it. And what another thing was there? Um,
That diagram's a final diagram. If you scroll down, where we merge the two
mm,
neurons,
okay, you know.
we get that pillar. That
I understood. So maybe what we can do is, mm, uh, we go to the so yeah, okay. So one is this. So say final thing before we go to final diagram. We should understand this also, right? That um, so one sigmoid will be, oh, this will have, yeah. So see, one sigmoid will be like this, right? In one direction. The another sigmoid we uh, yeah. Another sigmoid I want is opposite to it. So that I can subtract it and get a tower, right? So another, say I want it like this, and I can increase the weights as much as I can, and then I will get it as a very similar to step function. So this is a step function. I want it to be as much as possible to a step function, so that I can get the perfect tower. Will not get perfect tower, but we can get very near to it, right? So that is the whole idea. And then another I can do like this, and then if I subtract both of the sigmoids, I'll get this one tower. So this is my one tower. and several of this tower I have to add, right? So that was the idea behind it, that to get the function.
So,
So
so
this
sorry
how
to
I'll get.
sorry to interrupt,
Mhm.
but I think both the sigmoids were in the same direction, but with a little distance apart, not
Uh,
the above and below. I mean the reverse one, because for this diagram, if we check, the
okay.
tower will be upside down.
Okay. No. See. They.
Uh,
Okay. So you can see this minus here. H11
Right,
minus
I am
is
no, no, I am
so that.
saying that only. For the
Okay.
diagram that you drew just now, in the center portion, both the sigmoids have a value of 1, right? So in the middle, we get a 0. To the left side, one sigmoid has 1 and another has 0, right? So to the left side, we have a 1. To the right side also, similarly, one has value of 1 and other has value of 0. So subtraction in the left and right will give you a value of 1, whereas in the middle, the subtraction value will be 0. So this will be like a dip, not a tower.
Uh, okay. No, I was actually thinking with respect to H21 or something like the final thing, but okay, that is also okay. Okay. So you can say, you can maybe think that way also. That what I have is that I have one sigmoid and then another sigmoid, and how will I get this on the center portion? So
Yeah,
that for
in
that
the
I have to
center.
subtract it, right? So
Yeah, in the
subtraction will
center
happen.
it will give 1 minus 0, so that will give a tower.
Yeah. So how will I subtract it? I have to flip it, right? So flipping is subtracting of it. So then only I can subtract, right?
Okay, after flipping, you do addition. You just
Yeah,
take
you
minus
addition.
H12
Flipping
and
and addition or subtraction, both are same. Yes.
okay, okay.
Right? So this flipping will be controlled by this minus sign, H11 minus H12.
Minus.
Okay. So this flipping
Okay.
and then addition or subtraction. You can think both the way, but that is same. So yeah, so this multiple of the towers you can get, and then you can add them up, and finally what you'll get is this function thing, right? You can approximate it as good as you want using this tower. So more towers you create, the better the approximation, right? So that is the whole idea of it. Now this is just in, like, maybe you can say a 2D tower, or just because of like uh, I think this naming has a little bit here and there, but uh, okay, so this naming will be a little off, but you understood point, right? That sometimes they say 2D, sometimes they say 3D tower, but what I exit. Uh, so they consider so in this we will consider the dimension of tower based on the number of parameters we are considering, or parameters we are going to consider. So one sigmoid function, how you can do is wx plus b, right? So we have one w, um, something like that, right? So this one sigmoid you can draw with like one e power minus, or let's say minus z, where z is w x plus p, right? So this w is one only. That's why we maybe call it as 1D tower or something. When we'll have two W1 and W2, we'll call it as 2D tower. And then more than that, it will be 3D tower, I think. And that's how it goes. So that's how they did it. And then we subtraction and all we do, but that is okay. So uh, that will also do. Okay, so I'll go to this part. So this is yeah. So that's what I'm talking about. That this is the 2D tower, right? So now you want two weights. You require two weights to make this, and yeah, that's what this is 2D tower. Okay. Uh, this was 1D. Now, so we had one feature. That means one W, right? One feature, one W. More feature, more W. So we have two features now. One is, let's say, salinity, and another is pressure. So two features are there, and for those two features, I wanted to plot this thing, this towers, right? So how will I do it? So since there are like two features, and how will I do it? Uh, like uh, this is not a square, this is cube, right? So cuboid, you can say cuboid is there. That's what I wanted to make. So how will I do it? So first thing, I need some flat surfaces, right? So flat surfaces I'll require. Earlier I had like flat lines. So towers step functions used to give me this lines only, right? So this is just a line, but this now I don't want line. I want something like you can say in 3D, you can think like maybe a surface I want. So the surfaces I can get using the another W. So this part I can get using W1. With this I can get using W2 inside, right? So that's where I'll get flats and all. And now see this one, maybe you can say this kind of sigmoid. Okay, so this sigmoid, and another sigmoid is, let's say, uh, like this, like this. Something, and then you subtract out of it. So what you will have is, uh, you will have this as something like this, right? Something which is which is open from front and back, but it is filled from here. So like this. So this will be the whole thing will be like, so this was also like it has a surface and all. Okay, so it was filled. So now front and back is open, but it's like covered from two sides. So this thing you can able to achieve using two sigmoids. Okay, remember, two sigmoids, you are able to achieve this. The sigmoid has one sigmoid function has two uh, weights to it. So W1 and W2 you maybe consider. So same two weights or something like that has for both of the segments. Okay. Now you want two more sides. How will you do it? You will just do it another way. So more two sigmoids you will require. So two more sigmoid and you are done. So this two more sigmoid in another direction you want. So the direction and all you can control using W's, right? So W and B's you can B you can do for shifting, and W's you can have for uh, changing the direction of it. So
W
that's
is
what
for that curvature thing, no?
curvature also, and it will give direction also. So earlier we had only one, right? But now we want two. Uh, we can go there. So let's say uh, this one. Okay. So let's say this is the one I want. Now I want in another direction. What I can do is, see, you can currently see this one direction, right? This is a surface. Now let's say if I reset it and I would have increased, and you can see, can you see it's in the another direction, the uh, surface,
Yes. Hmm.
right? So you can control using W's that which direction you want this um, shape. Okay, so using this two, um, you can have it this way or the perpendicular to it. Okay, so and this W will okay, and W will do the shifting, right? So I think we okay, so the uh, shifting is happening, but it's very small. Like
W2 is 0 actually. So zero.
no, see, W2 is 0, but um still like it will see, shifting is happening in like uh,
I think it's B. We will have two biases, na. So
uh,
I think
uh,
it is B1 something. So maybe
no, we won't have two biases. We'll have only one bias. So this is one sigmoid now. You can think this is, we have two weights and one bias of one sigmoid. So this is one sigmoid currently representing. And using one sigmoid only, you can achieve this thing, this shape. This shape you can achieve using one sigmoid. So this is one sigmoid. It has multiple weights now, right? So earlier we had only one weight, right? So if you had like one weight, like e minus z, so this z is there, and z is, if it is wx plus b, then you will get the line only, this thing, right? This line, um, or, or like this. But what now we want surface. So what we did is we had w1 x1 plus w2 x2 plus b. So these two weights are there and one bias. Bias will again control the shifting only, and weight will control the orientation of it. You can think in this way, and any way you can orient it. You can using w1 or w2, and that's how you get the whole thing later on. So you'll use four kind of sigmoids. So one sigmoid will be opposite to this, and then two sigmoids, like maybe you can say not opposite but 90-degree to it, something like that. And finally you will get the whole tower, a cuboid tower. Okay, so this is using two sigmoids. So currently I am using two sigmoids only to get this. One is h11, one is h12, you can think. So um so I have this, subtracting it, and I'm getting it. Okay, now maybe here if I do b1 and b2, you can get the uh, shift, uh, like this, right? So
Each
so you
B1
can
for
see,
each. That.
yeah, each b is for each one, right? So how much you want it. So in
Hmm.
that, what was happening is the graph was, um, even the b, I am shifting it, but there was no reference point, so it was not visible. Could be. But here we have the another segment as a reference, that okay, how much far I'm going, or how much towards I'm moving it, to that. Okay. So like this, you can have the tower, and this is tower from two sides. Now we want more two sides, right, to be filled up.
In
So
that
two more
direction, yes,
huh?
yes.
Yeah. So two more sigmoids I require, and that I'll do using this. So now I'll have the h1 h11, h12, h13, h14. So this two will give, you can see here, h11 minus, okay, h11 minus h12, which will two side. I think
And
this
by
will,
default, that direction has been
so
allotted
just,
such that we will cover the front and back from the second angle.
yes. So this way you can cover this two, and this way you will cover the other two sides, right? The
Hmm.
flaps. So now you want a box of it. So how will you get this box size? You will sum all of them. So this this you will sum, and um, you can see this thing you can get, right, uh, filled up.
The box below that open box, na?
So
Brown open.
this, no. So see, summation is, what is happening is, uh, just focus that when, I think when everything is zero, so like this, 0 point, right, which is origin. You can see origin there. Both the functions will have value 1. Okay, moving out and so on. For some reason. So so if you do the summation of both of them, what you will get is, you will get, mm, okay, some just there. Let me- Yeah. So this is what summation is looking like. So where you can see the size is little higher than the rest of it, this part, right? So this middle part, right, near origin, or near Z, right? This is where the value of my, all the things is 2. But I don't want it as a, summation as 2, right? I want it as in like under 1. The reason is so that I can control the towers later on. So this, all the towers size will be something, right? So that I can get using, uh, something. So here you can see maybe they shown 0.5.
Like, is it again passing it through sigmoid
Uh,
to get it under
yes,
one?
again passing through the sigmoid to control the size of the tower. So this height you can get as much like how many you would add. So here I'm adding two only, so I'm getting two height. If I add multiple towers, three, let's say if it is going to be in, let's say 5D, right? So five currently it's in um, 2D tower. So if it's 5D tower, then the maximum tower height we'll get is 5. But we wanted to control the sizes, so we'll send all of this to another segment, which will add and maybe control the size also. So this thing all will come across like some size. Okay. So this three four thing you can do. So here is okay equations. I'm not sure if this equation is correct, but this is what we are doing it actually. So sigmoid, second sigmoid, third, fourth. We are having one subtracting another from it. So we'll get two sides. Then we get two sides. Then we add both of them, right? So wherever both of them are positive, you will get higher that, right? But we can trim it off. So trimming is done by the another sigmoid. So this trimming is what another sigmoid is doing. You see, if you don't want to trim it, then maybe summation was enough, right? But trimming is what required, and the trimming part will be done by this another sigmoid.
So could you move that to the visualization part again, and which part we trimmed actually? If you could see some
Yeah.
in the sum.
See, sure. Okay, see this. I'll show you. This is one, right?
Hmm.
So check near Z. Okay, this is another. So you can see where both of them are one. If you add them, what will happen? Okay, again, it lost. I don't know why it's not coming correctly. See, we go this is the one. Here again. So this is one. Okay, and this is another, right? So you can see where both of them are. You can say one, or here you can see both of them are there, right? So if I sum them up, why it's not accepting? Yeah. So this part, right, where both of them are maybe you can say uh, inside each other, right? So this near Z1, where
That.
both of them. So
Hmm.
if I sum them up, you can see. Can you see the bump is there a little higher?
Yes. Hmm.
That bump I don't want. I want to control the size of it, right? Because as many sigmoids or as many dimension increase, that bump will be that much higher. So it has
So
to be controlled by something. So that controlation part is by the another sigmoid. So that thing you can see using this tower, another tower. You can see inside it. So you will get this part inside, right? So another
so
controlation is
in
by
that
the next sigmoid.
part, sir, when we had that sum one, so
Hmm.
basically our tower was from beneath to the bump one, including that bump one. That whole was our tower,
Yes, yes, yes.
and now we
Now if I
managed
just,
to
yeah,
uh,
using the sigmoid, I can control the size of it.
control that from 0 to 1. We did that. Okay.
Yes, 0 to 1. I'll have it, right, because another sigmoid will give from 0 to 1, right? The range of sigmoid is 0 to 1.
Hmm. So, from the visualization perspective, actually, I'm not sure. What we did earlier is that when we had the difference, first two difference, we had open space from front and back.
Yes.
So, if you continue this uh, analogy, and
Hmm.
so when we see the sum, if you can click that the sum one,
Hmm.
so again, is it open from upside, that bump?
No, no, it's not open from outside. It is closed.
Okay, so that whole the thing is the tower, including the
It
bump,
is,
and we got okay,
yeah, it is actually closed. It's not thing. I think there's some mistake, but it is closed. Okay,
okay. Now it's
you
there,
can
sir.
you can see here it is
It
closed.
is closed. So we reduced that tower, including the bump, to a range between 0 and 1. So
Yes.
yes, fine.
Okay. Uh, fine. Um, and so this is what you get, right? So one dimensional. So dimensions comes from the sigmoid one, right? You understood this. Two dimension means two features are there. I have two features, and then three or more three dimensions. So three features. Some more features will add up. So so then like uh, how many neurons will you need to construct a n dimension? You can answer that, right?
Is it working in that fashion, 2 to the power n?
Yes, yes, that will be 2 power n, right?
Hmm. Okay.
Uh, yeah. Anything else?
Clear, sir. Like, if anyone don't have doubt, like I have from another concept, actually, not from week two. If not, no one has to ask anything else.
Okay. Uh, yeah, maybe you can ask. I think.
Okay.
Does anybody else have doubt in week two? Maybe you can go ahead. Whatever your doubt is.
Okay. So, sir, so it was regarding that gradient descent variants. So, uh, first one was the basic one where we do the gradient descent. After that, we move to that momentum based.
Hmm.
So, momentum based was I was able to get it that we were taking decision based on that how we moved in the previous, giving weights to the history.
Hmm.
But after that, when we went to that accelerated one, like going
Okay.
based on history only, we can overshoot, like oscillate more.
Hmm.
So on that accelerated path,
Hmm.
I was not able to connect that mathematical equation, that how we were looking forward, like look before you lean, that was used there. So in the
Uh,
mathematical expression, like in the momentum based, in the mathematical expression, I'm also able to connect that yes, we are going in a direction where we were suggested. So it was appearing in the equation also. But in the accelerated one, I'm not able to connect that how we
hmm.
are looking in the, like looking behind, and
Okay.
then we are making the decision.
Okay. Okay. See, this structure five, right? Um, let SGT. No,
Momentum
that's
basis.
we have to- okay. So this
Huh.
is nest rover.
Hmm.
So okay. See, I understood the point why the issue is there. The one issue which happens is since let's say you have this value, right? Um, so this is the loss value you have, and if I tell you, let's say your function is any function. I mean, just consider that this function is let's say p comma q, right? And then you have value. If I ask you, give me the derivation of this function with respect to p, can you do it? If it's a continuous function, you you can,
Huh.
right?
Huh. Yes.
You can do it, right?
Hmm.
Now, see, the issue happens is this. So this is actually delta. You can say loss with respect to wt minus whatever, right? So
Hmm.
this
Hmm.
uh, this is what you wanted to find out. So how will you do if you don't know the loss value at this point? I mean, I mean, so see, let's say if I give you p, this f of p, and if I ask you, can you give me the derivation of this with respect to q? Can you do it? If it's not the function of p, it is not, if it's not function of q. Sorry, can you do it?
It is
Is it?
not the function of Q.
Yeah, it's
Uh,
not a function of q.
then how we will do that? Like P should be connected. Then we
You
how?
can't, right? You can't.
You can't. Huh.
Yeah, yeah. Let's say it is connected, then you can. But if it's not connected, then you can't, right? So this is in this case, in NAG case, it is connected, and that connection is what this part is. So first point you have to do is uh, so I think it is in the not sure if it is, uh, but I don't know about this what a code is written. If you read that code carefully, you might be able to get it. But that's okay.
Oh,
So first, what we do is first we find the function value at this point, this wt minus beta thing. Okay. So what is that function value? We take the derivative at this point, gradient, and then I do this thing. Okay. I
gradient at
move.
the current step. First, we are making figuring out at
Yes.
the current step.
So, yeah. So another thing is this part, right? The movement part. Okay. Okay. Let's say this was there. I know my loss value at this point. Now I'll move by something which is beta.
The history
This
of the
beta
previous
ut
one.
minus one,
Yes.
right? So
Hmm.
this part I moved. Now this
Hmm.
part, where is it? How will I know where is it? I will find the loss function value at this point, right? I'll first calculate the loss value at this point.
Ah.
Once I know this loss value at this point, now can I take the derivative with respect to this thing? The whole whatever is inside. Can I do it?
Now derivative with this. Uh, yes. WT and okay. Since we have calculated for beta ut minus one, so with
Hmm.
respect to that, we can take.
Yes. So first, see, let's say your weights for something, you moved by some beta thing, right? Beta ut minus one. So what you will do is first, so w minus beta ut minus one. This is the point. These are the new weights you can consider. You can say maybe w2 is this. Is it okay?
Okay.
So at W2, you will again compute the loss. That is also okay. You can compute it the loss.
Okay.
Now,
Computer.
if I tell you to give me the derivation of del L by del W2, can you do it?
Okay. Yes. Huh.
So this is the what this is what you are doing in it. This,
Okay.
yeah,
So.
you can consider this negative part as another W, maybe midpoint W, right? So whenever you do gradient descent, right? So let's say you are here, W1 is there. Okay, now you moved by this by something, and now you are W2. So this W2, what is this W2? This W2, maybe you can consider this is W1 minus beta ut minus 1. Is it fine? You can do that?
Oh, that is the part.
Yes. So that is the catch. If you understood this, then maybe you'll understand that how this is happening.
So
Okay.
basically, WT, WT. Okay. So like we were doing. Okay. Like we did we separated the thing like the history part like that first one in the first line UT beta UT minus one.
Hmm.
That is the thing which was associated with the momentum one. It is capturing that thing,
Yes.
that history how we were moving.
Yes.
But instead of updating directly with the second part,
Hmm.
uh, we are again uh, inside
Computing the
that we
loss.
are okay and again taking that beta ut minus 1
Yes,
for
yes.
that
So
one.
again, so this beta ut1 minus 1, I think it as a W2. Okay. You can think it that this is another W2. So actually what we are doing is we are in one cycle, we are updating two times.
Mm.
Okay. At this point, this NUT, which we'll get later. But first we'll update by this point. Okay. So the cycle or the loop will be one, but updation happens like you can think two times it happens. Okay.
so,
W will
so
change two times.
so regarding that part like we are looking ahead checking and we again come back so like can you just explain it again with the diagram how professor was trying to
What? Okay, how looking ahead?
Like professor took a convex function and he was trying to
So okay, so see the thing is, let's say you are here. This is my W initial, like W naught you can consider.
Mhm.
I moved by some part which is beta ut. Okay,
Up to
u
this it is clear. It is like momentum based. We did.
yeah,
Huh.
right. So momentum based. Now I'm here. Now I wanted to again do the derivation computation, right? So
In momentum also we had some movement like with some history and also with the change gradient one. Two kind of movement we had there.
yes, yes.
Hmm.
Uh,
So first
so
part we did that same as that momentum one, like
yeah, first
taking
part
up
we
the
did
history.
same as momentum one.
And second part we also do some movement, but that would be regarding the change or the gradient one,
Hmm.
like.
No, see, this beta UT now it looks like so. See the new UT which you are seeing here.
Hmm.
This UT is little different in both the cases. See, here you can see it is uh, like these two components. Earlier it was little different, which is uh,
The
which
momentum,
is like this. Okay, so what I'll
like
do is
we had two kind of progress or step what we were taking. One is the history one, that what history we
yeah.
had.
So
And
history one we have again, right? But now
again,
this gradient thing is
that
different.
gradient thing we took up that directly in momentum, like whatever the gradient thing we had, like this is same as the simple gradient descent, what the gradient hit with eta we had.
Yeah, yeah. So
Hmm.
this is like simple gradient descent,
Hmm.
right? So see, when so in this case, what we're doing is we were here. This is the point I was present. I will move by the momentum and the gradient, right? Momentum and gradient.
Yeah, two
So
components. Hmm.
two components, but together. Okay, together I'm
Together,
doing.
yes.
In new case, what I'm saying is that let's say this was loss. I'm here. First move by momentum. So this is what I reached here.
First component,
Okay,
yes.
so now I'll move in another thing. I'll move by this the gradient part. So this is gradient and this is using momentum.
Two components, two movements,
Okay,
yes.
yeah. So two movements is neg. This
Hmm.
is what neg. This is both of them together. So both of them together is just momentum based.
So both of them together, two moment is the momentum, right?
Yeah, this is momentum. So
Huh.
together both of them momentum based gradient is.
Momentum, yes.
We
And
do
neg.
separately and that is what neg does.
Okay,
Okay.
so in that, sir, if you could like explain it again, like the nag part, like the second one where we had that movement, the gradient one. So
Okay.
what we did there for the gradient one, for the
So we
second one.
again compute the loss. Okay. So that's what I see first. See, do you know loss value here? Initial
Mhm.
loss value you know, right?
Okay,
Okay. Now you move by this using momentum. Fine.
momentum, first
You can
component,
do that.
yes. Hmm.
Now again you will compute loss here. Can you do that? Yes, you can
Yes,
do that, right?
we
So
can do
again
that.
you can compute the loss. Now you will do compute loss again. Then you will not update the weights. Okay, you will not update the weights. Just compute the loss. Fine.
Okay.
Not updation of the weights. Just compute loss. Then move by the gradients. Whatever loss comes up, find the gradient, move by that, then update the weights.
Okay. So as far I've understood, can we say that first component was that the same as the history one, that the movement in the momentum we had, that
Yes,
momentum
yes. First
component first.
component.
The first
Yes.
component is that, and regarding to the second component where we move with the gradient one.
Mm.
So in that part, what we did, instead of taking that gradient directly, we again something did like momentum to it again, like not.
Just normal gradient. Normal gradient. Momentum is already covered, right? Once we did it, momentum part we did it. Now, now we are just doing normal gradient design. You can think of this way. But
If
at
you could
this point,
scroll up, sir, in the algorithm, yes,
this
uh, so in the second part,
hmm,
we are doing something again appearing to as like uh, it has beta ut minus one
hmm.
with
So
the.
see this is where we had W's, right?
Hmm,
And with W's you were able to find loss.
loss.
Is it okay?
Hmm,
Now you moved by this much.
hmm,
You are here
first
now. Now
component.
you have WT minus beta UT. Okay, this is here, and you'll again compute loss with respect to this. Then then only you can actually find the gradient of that, right?
Gradient of that. Okay, so
Because
from
yeah,
this part we will get to know what is the gradient, and after that we will proceed. That
yeah,
was not the same case in the above two, the simplest one and the momentum based.
yeah. So in simplest one, what we did is we had gradient from here. So see, we had gradient here
Hmm.
and momentum here only. So both of
Uh,
them we add and move, right?
hmm.
That's all. So we had gradient of this point, not this point,
Yes.
right? So this point, but in this case, I'm not actually doing gradient here. I'm doing gradient here.
First
Okay.
we are moving to a part by component one, that momentum based,
Yeah.
and after that we are doing that gradient thing there, and after
Hmm.
that we are again making the movement. So
Yes.
so
So here
since we
I
are
had gradient of this point, not.
okay,
Uh,
so since we are doing that gradient thing, taking it again, so it will again now make sure that we will not overshoot taking up the two steps together.
yeah. So it will make sure. Yeah. Right.
Like
So
taking the
now if
gradient
I
will make
yeah
sure na ki we will not
yes
go in the wrong direction, too far in the wrong direction.
yes correct.
Yeah. Mm, maybe like if we will do more numericals, like if I will practice more numericals, it will be more clear, I think.
Yeah. So just think that you have to so in this what we had to do in normal momentum, you have to compute loss once only. Okay. Once
Once
loss
only.
computed, you do the back propagation. But here you have to compute two times the loss. Like two times you have to do it. Okay.
Hmm.
Updation is one only, but computation is two times of the loss because at new point you are reaching and you don't know where what is the loss there, right? If you don't know loss there, you can't compute the gradients also. So first you
Ha.
compute the loss, then compute gradient, then you can do it.
Calculate the gradient in now I can I get it, I think absolutely fine. So since we need that in the first component we have beta ut minus 1, that's fine. In the second component we are calculating the gradient, but for the gradient you need the loss function at that point.
Yes, yes.
Hmm. Okay. Yes, sir.
Sir, can we continue? Uh, what what we can continue?
Can you continue in the next class? Okay. Actually, the class is over. No one had doubt. That's why I asked. So someone was asking if we can continue in the next class.
Uh, yeah, I mean
The
we'll
class,
have it. So in so next so in fourth week we'll again will I'll explain this. Okay, not an issue.
yes.
If you want, then today I'm just if somebody had doubt, I'm just clearing
Yeah,
it. That's
actually,
all.
like no one had to ask anything. That's why I asked.
Yeah.
Okay.
So if you have any doubt related to week two, you can ask just whoever has it. Not an issue. Uh, okay. Do you have any doubt, like further doubt?
Not more of knowledge. It's clear. Back propagation was thing was also clear. Like things were explained well. Just sometimes like when I do a gap, I suffer remembering that derivatives. Like,
Okay. Yeah, but that you will get with practice. That is nothing.
yeah, okay. Do you have any kind of trick or something like intuition through which you remember those derivatives? Like in the back propagation part, like derivative of the loss function with the weight or with the hidden layers. Lot of stuffs
Mhm.
we had.
Um, uh, okay, I'm not sure how I did it. I uh, kind of understood it, but what I can give you is I can maybe
Like understood the
give you
part.
my
Mhm.
so last term also I explained this gradient descent part, and then after that most of the student understood it,
Mhm.
uh, which I'll do it in next class. I'll do it.
Like this
But if
part
you
is fine. I was talking about that back propagation thing where we had
yeah,
derivative of loss function with with respect to hidden layers or the weights.
so I get it. That is little bit confusing.
Uh,
Mm.
like
I'll cover
derivation.
it in next. class the complete thing, but as of now, what I can give you is I can give you one video. Um, Maybe you can watch it as uh,
Okay.
like I recommend everyone to watch it.
Hmm.
Okay, just this one, which
Okay.
covers like if you have any doubts related to back propagation, maybe it will clear it. Okay.
Okay.
Um, yeah. Still, you have any doubts, you can come to next class. Maybe
Yes,
you can
sir.
point it to very specific thing what you have, and I'll take it.
Sure, sure. And one small thing, Karthik's sessions or PDFs, whatever we had, so will it be uploaded in the same fashion as we had in the MLT, like in the portal section,
Um,
like
yeah,
PDFs
that we
from
can
Karthik
do
sir?
it, right? That uh, yeah, yes, we can do that. Not an issue.
Okay, like I was trying to visit the video lecturer that actually
For
it was
okay,
pinned
so
in the.
yeah,
Sorry,
so
yeah.
for now, how it is shared with you? Is there any?
Actually, I visited that Gmeet link. There it was attached, but I was not having the access. It is mentioned in that this Gmeet
Calendar.
calendar. It is there. Right now, it is not shared yet. I thought to
It's
write.
not okay. It's not there in calendar. I
Yesterday, I was trying to access. I didn't have access. I requested also Karthik sir to provide me the access.
no. See this whatever is currently there is just the session something chat and something like that.
Below the YouTube, we have deep learning. The video link and the doc link is also there.
That
Yeah,
doc link is chat
chat
or
one.
something. Yeah,
Sir,
it's not.
before that recording we have only.
Yeah, recording and chat, but not
Hmm. Yes, yes, PDF. Sorry,
the
sorry. I
notes.
was accessing
Notes you
the
want
recording.
that is not good. Okay, okay, I'll see into it how we can give it. So the best scenario is that we add it in supplementary content as
Yes, the
a
supplementary
something,
part.
right? Folder
Yes,
and then edit. Yeah, that is
yes,
the
yes, sir.
way we'll do it. Okay, not an issue.
Okay, sir.
Okay, anything else?
Oh, not right now. Like,
Okay,
fine.
anybody else? Okay, fine then. So for next session, I'll recommend that uh, first you so the link I shared, maybe you can watch that. That is there.
Yes, yeah.
Another thing is there will be in one back propagation assignment given to you, practice assignment.
Okay,
Please solve that also. So try to solve it using without I mean without computer. Manually you can do it. You can try it at least. Using calculator is fine, but it's
okay.
consider that you have to do it in exam. Okay, and
Okay. That would be provided separately, like or in the portal.
it is there. Back propagation practice assignment one, something like that name is there, and it's there.
Okay.
Okay.
Haven't seen like this. Okay, okay.
Yeah, that's all. So that's all from my side.
Okay, sir. Thank you for the session. Actually, I got my doubts cleared. Like I had some of them. So it was a really good session for me.
Yeah, yeah, sure. Welcome. Most
Thank
welcome.
you, sir.
Anybody else has any doubt, or we can close the session?
Thank you, sir, for the valuable session.
Yeah, sure. Always welcome.
Okay. Good night, sir.
Yeah, good night then. Okay, I'll just closing it.